In this lecture, we will learn about implicit differentiation. So let's examine this example to understand the implicit differentiation. We have x squared plus y squared equal to 16. This is an equation of a circle. Well, we can write it as an explicit function. So we can rewrite this equation as y squared equal to 16 minus x squared. And we can also take a square root on both the sides, which gives us plus or minus square root 16 minus x squared. So now you want to read this expression y carefully. Y can be a positive expression with root or a negative expression with the root. If you try to plot the positive expression, it's the top part of the circle above the x-axis, and the negative part of the expression will be the bottom part of the circle. So I'm going to write it as the top and the bottom. So let me write the top part, y equal to square root 16 minus x squared. This can be written as 16 minus x squared, and then you have the exponent 1/2. The reason is it's nice and easy to differentiate if the exponent is written in the form of a fraction rather than a radical sign. So you want to write y prime equal to 1/2 16 minus x squared negative 1/2. So we did the power rule of differentiation. But please understand that we also have to differentiate the 16 minus x squared, which is negative 2x. Now let's simplify a little bit. I can cancel the 2 in the denominator and the 2 in the numerator and bring the negative out, write it as negative x divided by 16 minus x squared, but this time I'm going to write the negative 1/2 as a square root function. So let us differentiate the bottom part of the curve, which is the negative square root function. So I'm going to write y equal to negative square root 16 minus x squared. By differentiating, I have y prime equal to negative 1/2 16 minus x squared and then negative 1/2 times negative 2x, because I'm going to differentiate this again. Now I can cancel the 2's and I can write this as x divided by square root 16 minus x squared. The negative 1/2 exponent is written as square root. So there were two ways to differentiate the given function. First, write the given function in the form of an explicit function and then start differentiating. Now you want to compare this with implicit differentiation, which you will learn in this particular section. So x squared plus y squared equal to 16 is the given curve. And the question asks us to find the derivative, which means we want to find dy over dx. So we want to find this. So let me differentiate the given function, differentiation of x squared with respect to x. So how did we know with respect to x? You see the denominator term is x. So you want to differentiate with respect to the variable x. So differentiate x squared in the first go, power rule, you get 2x. Differentiate x again, it's dx over dx, so it's same as you not writing this. Differentiate y square, you have 2y. But differentiate y again, so it's dy over dx. Chain rule. Then you have 16, differentiate 16, you have 0. But we know that dx over dx is 1, so it was much okay not to write the dx over dx. You're differentiating x squared, which is a function of x, with respect to the variable x. So even if you differentiate x again, you will see that term becomes 1. So whenever you're differentiating any variable with respect to the same variable, you don't have to write a chain rule for that particular variable. Whereas for the variable y, when you differentiate, you have 2y, but this y should be differentiated again, the chain rule, and then you have dy over dx. So let's simplify this a little bit. I'm going to write this as 2y dy over dx equals negative 2x. I'm going to add negative 2x on both the sides. Now I will divide by 2y on both the sides. So I have dy over dx equals negative x over y. So this is the final answer what we have for the derivative function. You may feel that this is a little bit different from what we have derived in the top for the top and the bottom, but if you observe carefully, when you plug in this expression y here in the denominator as a square root function, either it's plus or minus 16 minus x square, then you can compare the answer on the top, it's the same. In the next example, you are asked to find derivative given an expression x cube plus 2y cube is 4 times xy. So let's start differentiating with respect to the variable x. So how do we know with respect to x? Your denominator is x. So write this expression as star and say differentiate star with respect to the variable x. Because we have dy over dx, we know that we have to differentiate with respect to variable x. Okay, so let's differentiate the first expression x cube. We have 3x squared. We did the power rule of differentiation. Then we differentiate x again, so it's dx over dx, so it's okay for you not to write it. Differentiate 2y cube, you have 6y squared. Again, we did the power rule of differentiation. But this time you have to differentiate the variable y again. So when you differentiate y, you have dy over dx. Then you have an equal sign, write an equality sign. Then you have 4 times xy. So you can group 4x in one place and y in the other, and then read it as a product of function. So it's a product rule. So you fix 4x, you differentiate y with respect to x, so you have dy over dx. Now you fix y on the other side and differentiate 4x with respect to x, so you have 4. So what we did here is product rule of differentiation. Now we are asked to find dy over dx. So let's try to group the dy over dx terms. We have two terms here with dy over dx, one here and one here on the right. So move all the dy over dx term to one side. So this is negative 4x dy over dx. I'm moving the 4x term to the left, so it becomes negative. On the right hand side, I have 4y. And I don't want this 3x square on the left. So move it to the right, it becomes negative 3x square. So we did a grouping now. This is a grouping step. We grouped all the dy over dx on one side and all the other terms on the other side. So now we can factor the dy over dx. You see a dy over dx here, dy over dx here. So factor it out. And you have 6y square from the first term, and you have a negative 4x from the second term. Then you have 4y minus 3x square from the right hand side. Just bring it down. Now you are asked to find dy over dx, so you don't want this 6y square negative 4x. So you want to divide both the sides by the same term, 6 square negative y square negative 4x. So when you divide this, you have dy over dx on the left equals 4y minus 3x square on the right divided by 6y square minus 4x. And this is our final answer. In the next example, you are asked to compute the derivative dy over dx given an expression of trigonometry and polynomials. So again, I want you to read the question carefully. You are differentiating with respect to the variable x. So write the given expression as star and then write differentiate the given expression star with respect to the variable x. So derive the first expression with respect to x. You have tan x cubed. When you differentiate with respect to variable x, differentiation of tangent function is secant function, so write secant. And the function is x cubed, so write exactly the same. Differentiation of tangent is secant. That's our first step. But we have not derived this x cube. So let us derive this x cube. Derivative of x cube with respect to x is 3 times x squared, the power rule of differentiation. And now we have to derive this x again. But derivative of x with respect to x is 1, so it's okay for you not to write. But if you want to understand, this is 1, so it's totally okay not to write that dx over dx. Then you have a negative sign. So let me write that negative sign. And then I want you to read the function carefully. It's 4x times y square. So it's product of two functions, hence the product rule. So I want you to open up a bracket. Fix 4x, differentiate y square. So you have dy over dx. When you differentiate y square for the first time, you do the power rule. So it's 2y. Now differentiate this expression y again. When you differentiate y again, you have dy over dx. Now you fix y square, differentiate 4x, and then you have just 4. So this is the power rule of differentiation for y square term, and in general what you do here is the product rule. Then you have an equal to sign, differentiation of cosine function. Differentiation of cosine is negative sign of the same function, so write y. But we have to differentiate this variable y again, chain rule of differentiation. So you have dy over dx. So you have two terms with dy over dx. This is our term 1 and this is our term 2. But for the term 1, you have a negative sign outside. So distribute the negative to both the terms. And after distributing the negative, let us group all the dy over dx on one side and all the other terms on the other side. So this is our grouping pattern. So we have a negative 4x 2y dy over dx on the left, and the dy over dx on the right. We want to move it to left, so it becomes a positive term with the sign y and a dy over dx equals, on the left we have two terms without dy over dx. I'm going to put a star mark in purple color. That's the first term and this term, these star terms. So let's move all these star terms to the right. So when we move it to the right, we have secant x cubed 3x squared. It's a positive term, but when you move it to the right, it becomes negative. And you have a 4y squared with negative term. So when you move it to the right, it becomes positive. So now that we have grouped all the terms, dy over dx on one side and all the other terms on the other side, we are good to factor the dy over dx terms. And then we have 4x times 2y, which is negative 8xy, positive sin y, equals negative secant x cubed 3x squared, positive 4y squared. Now let's divide both the sides by these coefficients of dy over dx, which is all this term. We don't want this. So divide negative 8xy, positive sin y, on both the sides. So we have negative secant x cubed 3x squared, positive 4y squared, divided by negative 8xy, positive sin y. So this is the final format of the expression for dy over dx. And these type of differentiations are called as implicit differentiation. Compute dy over dx sine 2y e to the x squared cosine x cubed plus y squared. So again, I want you to read the differentiation carefully. You're finding the derivative of expression y with respect to the variable x. So you want to differentiate the expression with respect to x. So when you differentiate with respect to x, I'm going to write with respect to as w dot r dot t. This is with respect to. Differentiate with respect to the variable x. So on the left hand side you have sine 2y times e to the x squared. So I want you to read this as the product of two functions. Sine 2y is your first expression, e to the x squared is your second expression. So reading is really important. So read the expressions carefully. So fix the sine 2y term and differentiate the exponential term. Differentiation of exponential is the same, so write the same. But it's not a pure x, but rather you have an x square, so you have to do a chain rule. So differentiate x square again, you have a 2x. Differentiate x again, but you have 1, so it's okay for you not to write again. It's dx over dx term. Then you have we are doing a product rule. We did fix one term and we're differentiating the other. So let me write a plus sign. The plus sign comes from the product rule. And this time I'm going to fix e to the x square. I'm not going to differentiate this, but rather differentiate the sine 2y term. So when you differentiate sine term, you will have a cosine term, the same angle 2y. But differentiate 2y now. When you differentiate 2y, you have to chain rule of differentiation. Then you have an equal to sign. Differentiation of a cosine function is always a negative sign function. Sine of x cubed plus y square. So now we want to derive the inner function. So move inside and derive this inner function x cubed plus y square. So let me add a step here. This is a messy term, so you want to explicitly write what you're deriving and then derive it in the next step. So we are deriving x cubed plus y square with respect to the variable x. And this step is called as the chain rule. We derive the outer function and then we are deriving the inner function. So now let us derive the right hand side here. We have a negative sign product x cubed plus y square. Derivative of the first term with respect to x, you have 3x square, the power rule of differentiation, derivative of y square with respect to x, first derive y square, which is 2y, power rule, and now you want to differentiate this y again, chain rule. So it's dy over dx. Now you read carefully. I think we missed one term here, so let me add it. We did derive sine 2y, we got cosine 2y. We did derive 2y, we got 2. But you have to be a little bit more careful here in deriving this cosine term. It is 2, but what about derivative of the variable y with respect to x? So make sure that you add a dy over dx here. You do have to derive y also, so let's write dy over dx. Whenever you see an x function, derivative of x with respect to x, it's 1. But whenever you see a function y in the implicit differentiation, you have to derive it with respect to x. So we missed deriving the variable y. So I'm going to add a dy over dx term here. Now you read carefully, you have two terms with variable y. One is this term and the second one is this one. So you multiply out this term to both the terms and then you group all the dy over dx term. So dy over dx on one side, the coefficient will be cosine 2y times 2, and the dy on the dx on the right hand side, when you move it to the left, it becomes positive sine of x cubed plus y square, and then you have this 2y. Now move all the other terms to the right hand side. You have a negative sign expression on the right, which is multiplied by 3x square, and then you have a sine 2 term from the left, which you want to move to the right. So it is 2x sine 2y e to the x square, but this comes with a negative sign. So with all this, you see that you want a derivative term dy over dx, and you don't want all these expressions in the square bracket. So divide both the sides by this expression on the square bracket. So you have dy over dx equals negative sine x cubed plus y square times 3x square negative 2x sine 2y e to the x square divided by 2 cosine 2y plus sine x cubed plus y square times 2y. So this is our final answer. In the next problem, you are asked to find derivative and also compute its value at negative 1, 1. So you are given an expression x equal to, let me cross multiply this. Whenever you have a fraction a over b, c over d, the best way to simplify these fractions are cross multiplication. Multiply AD and BC. So you can write this as AD equal to BC. So let's do the same. It's x times x minus y equals 3 minus y square. Multiply out x square minus xy equal to 3 minus y square. Now start differentiating. Again, you understand that the differentiation variable is x. So differentiate the first term x square with respect to x, you have 2x. And then differentiate x again, it's 1, so it's okay not to write. Then you have xy term, so you do a product rule for this x times y term. So open up a square bracket, fix the first term x, differentiate the second term y. Differentiation of y with respect to x is dy over dx. Product rule always comes with a plus sign, so write plus. Now fix y, differentiate x with respect to x, you get 1. On the right hand side you have 3. When you differentiate 3, you have a 0, so don't write it. And then when you differentiate y square, you have negative 2y, power rule of differentiation. But don't forget to differentiate y again, the chain rule, dy over dx. Whenever you are differentiating the terms with x and y in the implicit differentiation, if you come across a term with x, you just do the respective rule, trigonometric differentiation, exponential, or the power rule. You don't have to differentiate x with respect to x again. But when you come up with an expression with y, you have to differentiate y with respect to x. All you're saying is y is a function of x, so you're going to derive it with respect to x. Now you read this carefully. You want to find dy over dx, and you have that in these two expressions, dy over dx, dy over dx. So you want to group all the terms to one side with dy over dx. So I'm going to write negative x dy over dx, positive 2y dy over dx. I moved all the dy over dx to one side. And I have a 2x on the left, move it to the right, negative 2x. I have negative y on the right, move it to the right, it's positive y. Now you're good to factor the dy over dx on the left. So you have 2y minus x equals negative 2x positive y. You want to find dy over dx, which means you don't want the terms in the bracket. So divide on both the sides by this term. So you have dy over dx equals negative 2x plus y, and then you have 2y minus x. But you're asked to evaluate the expression at 1 and negative 1. So plug in 1, negative 1, 1. So plug in on both the sides by negative 1, 1. So x value is negative 1 and y value is 1. So when you plug in, you have negative 2 times negative 1, positive 1 divided by 2 times 1 and then negative of negative 1. Simplify, you have negative 2 times negative 1, 2, 2 plus 1, 3 on the top. Then you have negative times negative 1, positive 1. So 2 plus 1 is 3 on the bottom. So answer is 1. Then you have a inverse trigonometric function and you're asked to find the derivative dy over dx. So let me draw a triangle for this inverse trigonometric function. Let me write this as an angle y. This ratio is x and this one is 1. So here, suppose this is an angle y and the ratios are x and 1. Using the Pythagoras theorem, I can write this as 1 minus x squared. So now I want to figure out the cosine function from this, but because you will see a cosine function when you start deriving the problem. Cosine will be adjacent, which is 1 minus x squared, by the hypotenuse 1. So it is 1 minus x squared. Now let's get back to the problem. You have an expression y equal to sine inverse x. You can also call this as arc of sine of x. Now, this is equivalent to writing sine of y equal to x. When you do a sine on both the sides, you have sine y equal to x. Now you're good to derive this, so let's derive it. Because derivative of sine with respect to variable x is cosine y, dy over dx. Derivative of x with respect to 1 is 1. Then you have dy over dx equals 1 over cosine y, but cosine y is square root of 1 minus x squared. So the derivative of the given expression is 1 over square root of 1 minus x squared. So this idea is used to derive the inverse trigonometric functions, and here are the formulas for derivative of sine inverse, cosine inverse, tangent inverse, and the reciprocal ratios, sine cosecant, cosine secant, tangent cotangent. So they vary by a negative sign from the left. Find the derivative of y equal to sine inverse of 2x squared. So we can write this as arc of sine of 2x, and then you have a square. So now let's derive this. Derivative of y is y prime, which is same as dy over dx. First we see this exponent 2, we do a power rule. So it's 2 times arc sine of 2x, and the new exponent we have is 1 times. Now we want to derive arc sine, and we have the formula on the top. Derivative of arc sine is 1 over square root of 1 minus x squared. So we're going to write this as 1 over square root 1 minus x is 2x here, so write it as 2x and then the square. But it's not just pure x here in this place, but we have a 2x, so we have to derive this again. Derivative of 2x is 2. We can simplify this a little bit. We can rewrite this as 4 arc sine 2x divided by square root of 1 minus 4x squared. So this is our simplified answer. In the next example, you have cosine inverse of 4x squared. So you can write this as y prime, which is derivative of y with respect to x. Derivative of cosine inverse, we have a formula here on the top, is negative 1 over square root 1 minus x squared. So I'm going to write this as negative 1 over square root 1 minus, in the place of x you have a 4x squared, so write whatever is the angle and then square it. But you have to differentiate this 4x square again, chain rule, which is 8x. And this is equal to negative 8x divided by the square root of 1 minus 4x squared, the square function. In the next example, you are given arc of tangent of sine 4x. So let's derive this. I'm going to write this as a y prime. Derivative of tangent function, arc tan, we have a formula here. It's 1 minus 1 divided by 1 plus x squared. So it's 1 divided by 1 plus the angle. In the place of angle, tangent of an angle, the angle itself is sine 4x. So write the entire sine 4x and then square this angle. Now you want to derive sine 4x. Derivative of sine 4x is cosine 4x. Now you want to derive cosine 4, angle 4x. The derivative is 4. So we did a chain rule. Simplify. You have 4 cosine 4x divided by 1 plus sine of, you can also write the square inside rather than outside, and then 4x. But it's understood that it's sine of the angle 4x times sine of the angle 4x. Then you have x cubed secant inverse 5x plus 1. So I'm going to write the derivative of y as y prime. And I read this as a product of two functions. So it's the product rule. The first function is x cubed. The second function is secant inverse of the angle 5x plus 1. So fix x cubed, derive secant inverse. Derivative of secant inverse, the formula what we have here on the top, is 1 over the angle x times x square minus 1. Whatever is the angles come down here in this pattern. 1 over x times square root x square minus 1. So the angle here is 5x plus 1. So when you derive this one, you have 1 over the angle 5x plus 1 times square root 5x plus 1 the square, and then you have a negative 1. But don't forget to differentiate this 5x plus 1 again, and you have a 5. So this was just one part of the product rule, just one term. This is your u, this is your v, so all we did was uv prime. So now we have to do, we have to fix the v and then we have to derive the u prime. So when we fix the v, all we have is v is the secant function, we are not going to touch that, but let's differentiate u. Differentiation of u, x cube. Differentiation of x cube is 3x squared, the power rule of differentiation. So this is your final answer after all this hard work of learning chain rule, implicit differentiation, and the trig differentiation. So we'll end this lecture here.